Hello everyone, welcome to our channel Clear and Concise. In this video, I am explaining you ISRO Mechanical Engineering previous year questions with solutions. Let's have a look at this question. In nodular iron, graphite is in the form of option A cementite, B free carbon, C flakes, option D spheroids. The correct answer is option D spheroids. Nodular iron belongs to the class of cast irons. In cast irons, carbon content is between 2 to 6.67%. The carbon present in the free form in case of cast irons. Cast irons are broadly classified into grey cast iron, white cast iron, malleable cast iron and ductile cast iron. In grey cast iron, carbon presents in the form of graphite flakes. In white cast iron, carbon presents in the form of cementite. In malleable cast iron, carbon presents in the form of graphite aggregates, whereas in nodular cast iron, carbon presents in the form of graphite spheroids. Addition of magnesium to the white cast iron converts graphite flakes into spheroids or nodules. The presence of spheroids or nodules increases the ductility of cast iron. That's why nodular cast iron is also called as ductile cast iron. Moving on to the next question. Hardness of steel depends on option A amount of carbon it contains, B the shape and distribution of carbides in iron, option C method of fabrication, option D content of alloying elements. The correct answer is option A amount of carbon it contains. Steel is an alloy of iron and carbon where carbon presents up to 2% in steels. Based on carbon content, the steels are classified into low carbon steels, mild steels, medium carbon steels, high carbon steels and tool steels. The hardness of steels increases with the percentage of carbon. So, low carbon steels are the steels with least hardness, whereas tool steels are the steels with highest hardness because the carbon percentage is higher in tool steels. Let's have a look at this question. Too high welding current in arc welding would result in option A excessive spatter, undercutting along edges, irregular deposits and wasted electrodes. Option B excessive piling up of weld metal, poor penetration and wasted electrodes. Option C too small bead, weak weld and wasted electrodes. Option D excessive piling up of weld metal, overlapping without penetration of edges and wasted electrodes. The correct answer is option A excessive spatter, undercutting along edges, irregular deposits and wasted electrodes. If welding current is too high, we will have small dots around the weld. Those are called spatters. So, if the welding current is too high, we will have excessive spatter around weld that needs to be cleaned off. Along with that, undercuts shown in the figure here leads to weak weld. So, we need to maintain proper current, voltage and speed in order to get a smooth, regular and well formed bead with no undercuts, overlappings or piling up of weld metals. In order to get uniform cross section of weld metal, we need to have proper current, voltage and speed so that we can have excellent weld at minimum material and labor cost. If not, if we maintain welding current is too high during the welding, then we will have excessive spatter, undercutting along edges, irregular deposits, wasted electrodes and production time as shown in the figure here. We can clearly observe excessive spatter here along with the undercuttings, irregular deposits, which leads to the wastage of electrodes and production time. If welding current is too low, here in the figure it is clearly shown that excessive piling up of weld metal and overlapping that leads to the poor penetration, which slows up the process ultimately, that leads to wastage of electrodes and production time. Apart from that, if welding speed is too high, as shown in the figure here, we will have two small beads with irregular contours that leads to not enough weld metal deposition in the cross section, which ultimately leads to weak joint. So we need to maintain proper speed, otherwise we will have lot of issues with the weld. If welding speed is too low, then we can see here in the figure excessive piling up of the weld metal, overlapping without penetration at edges, which leads to wasted electrodes and production time. Along with that, if voltage is too high in arc welding, then we will have irregular bead deposition with poor penetration, poor shielding of weld metal and inefficient weld. So we need to maintain voltage, current as well as speed in such a way that leads to sound weld. Moving on to the next question. Which of the following process would produce strongest components? Option A, hot rolling, B, extrusion, C, cold rolling, option D, forging. The correct answer is option D, forging. Generally, the components produced during hot working are ductile in nature because they doesn't undergo work hardening and there are no internal stresses in those components. When it comes to forging, compressive force is applied at room temperature, so it retains any internal stresses generated due to hammering and it undergoes work hardening during repeated blows. So it results in low ductility and high strength of the components manufactured using forging. Along with that, during forging, directional alignment of grain flow that results in strong and tough components. So the components produced in forging are generally strongest components. Let's have a look at this question. If a quantity Q is dependent on three other quantities Q1, Q2, Q3 related such that Q is equals to K times Q1 power N1, Q2 power N2, Q3 power N3, then overall error del Q by Q is equals to. So in order to find overall error del Q by Q, we can find the total derivative of multivariable function Q, that is equals to del Q, which is defined as dou Q by dou Q1 times del Q1 plus dou Q by dou Q2 times del Q2 plus dou Q by dou Q3 times del Q3. Here we are obtaining partial derivative of multivariable function Q with respect to each independent variable Q1, Q2, Q3. So first let's obtain the partial derivative of Q with respect to Q1, that is equals to dou by dou Q1 of K times Q is defined as Q1 power N1, Q2 power N2, Q3 power N3. While we are finding partial derivative of a multivariable function with respect to any independent variable, we treat other variables as constants. So we are finding with respect to Q1, we treat Q2 and Q3 as constants. Now let's take out constants out of derivative, then k times, because k is constant, now q2 is also constant, q3 is also constant, so we are taking out those terms. Then we will have dou by dou q1 times q1 power n1. Now we know derivative of x with respect to x power n, like derivative of x power n with respect to x is equals to n times x power n minus 1. By using this formula, if we apply to the above equation, we will have k times q2 power n2 q3 power n3. Now derivative of q1 power n1, which is equals to n1 times q1 power n1 minus 1. Now we know a power m minus n is equals to a power m by a power n. By using this formula, in the previous equation, q power n1, q1 power n1 minus 1 can be written as q1 power n1 divided by q1 power 1, which is equals to q1 power n1 by q1. So let's write this. Now we will have dou q by dou q1 is equals to k times q2 power n2 q3 power n3, which are constants, then n1 times this term q1 power n1 by q1. We know k times q1 power n1 q2 power n2 q3 power n3 is equals to capital Q, and we have now n1 by q1. Similarly, if we obtain dou q by dou q2, now we are finding derivative with respect to q2, so other terms q1 and q3 are constants. So k times q1 power n1 q3 power n3 are constants. Dou by dou q2 times q2 power n2, that is equals to k1 k times q1 power n1 q3 power n3, and now finding the derivative leads to n2 times q2 power n2 minus 1, again which leads to q times n2 by q2. Similarly, if we obtain for partial derivative of q with respect to q3, then we will have q1 and q2 as constants, q1 power n1 q2 power n2. We will have dou by dou q3 times q3 power n3, which leads to k times q1 power n1 q2 power n2, then n3 times q3 power n3 minus 1, again which leads to q times n3 by q3. Now substituting in the equation, we have total derivative del q is equals to dou q by dou q1, which is q times n1 by q1 times del q1 plus dou by dou q by dou q2, this one, q times n2 by q2 times del q2 plus dou q by dou q3, which is q times n3 by q3 times del q3. Now if we divide both sides with q, we will have del q by q is equals to n1 by q1 times del q1 plus n2 by Q2 times del Q2 plus N3 by Q3 times del Q3. So the correct answer is option A, N1 times del Q1 by Q1 plus N2 times del Q2 by Q2 plus N3 times del Q3 by Q3. Moving on to the next question. Which of the following has maximum hardness? Option A, austenite, B, pearlite, C, trustite, option D, martensite. The correct answer is option D, martensite. The structure of martensite is BCT, that is body centered tetragonal, where carbon is entrapped in between edges, which leads to high hardness and high stress fields. When austenite is cooled from 723 degrees centigrade, depending upon the cooling rate, it can form martensite, very fine pearlite, coarse pearlite. If it is quenched using water, it forms martensite. If austenite is oil quenched, then it forms very fine pearlite, which is also called as trustite. When it is air cooled, then it forms fine pearlite, which is also called as sorbite. If it is furnace cooled, then it forms coarse pearlite. When it comes to hardness, martensite has the highest hardness, followed by trustite, then sorbite, followed by coarse pearlite. Let's have a look at this question. The main advantage of line organization is its option A, effective command and control, B, defined responsibilities, C, rigid discipline, option D, all of the above. The correct answer is option D, all of the above. In line organization, the authority approach is vertical approach, where there will be a topmost authority, followed by managers, then followed by workers, like that. Then it is very simple to work and stable, that has accountability and low running cost. So the correct answer is option D, all of the above. Moving on to the next question. The mathematical technique for finding the best use of limited resources in an optimum manner is known as option A, operations research, B, linear programming, C, network analysis, D, queuing theory. The correct answer is option B, linear programming. The given thing is, it is a definition of linear programming. When it comes to operations research, it is a scientific approaches for decision making based on quantitative analysis. When it comes to network analysis, it is a technique to schedule, plan and manage projects by using CPM and PERT techniques. And when it comes to queuing theory, it is a probabilistic analysis of waiting lines to estimate the service times. So the correct answer is option B, linear programming. The given question is, it is a definition of linear programming. Let's have a look at this question. Which of the following errors are generally distributed in accordance with the Gaussian distribution? Controllable errors, calibration errors, avoidable errors, random errors. The correct answer is option D, random errors. Errors are broadly categorized into two types, random errors and systematic errors. Random errors are caused by unknown and unpredictable changes in the instruments or environment or measurements or whatever it may be. Like when it comes to systematic errors, they comes from the measuring instruments, can be easily controlled and eliminated by taking proper care. When it comes to random errors, it is very difficult to predict the reason and eliminate them. Moving on to the next question. PL cube by 3EI is the deflection under the load P of a cantilever beam having length L, modulus of elasticity E, moment of inertia I. Then the strain energy due to bending is, strain energy U is equals to half P delta, where P is load, delta is deflection. So substituting that, half the load on cantilever beam is P and the deflection is PL cube by 3EI, which is equals to 1 by 3 2s are 6, then P square, P times P square L cube by EI. So the correct answer is P square L cube by 6 EI. Option B is the correct answer. Let's have a look at this question. A mass M is attached to a light spring which oscillates with a period of 2 seconds. If the mass is increased by 2 kg, the period increases by 1 second. Then the value of mass M is. So in the problem, initial mass M1 is M kg, time period T1 is 2 seconds. Now the mass is increased by 2 kg. So final mass is M plus 2. Time periods increases by 1 second. So 2 plus 1, 3 seconds. Now we know time period T is equals to 1 by F, where F is natural frequency of the system. At the same time, we have omega equals to 2 pi F. So rewriting this yields F equals to omega by 2 pi, and we know omega is equals to square root of k by m. So square root of k by m times 1 by 2 pi. F is defined as square root of k by m times 1 by 2 pi. Now substituting that in time period yields T is equals to 1 by F. So if I substitute that, we will have 2 pi times square root of m by square root of k. This term 2 pi by square root of k is constant. So I'll replace it with some term C. So because 2 pi by root k, where k is spring stiffness which is constant, so I am replacing the whole term 2 pi by root k as some constant and square root of m. Now I can square both sides to get t square is equals to c square. So it doesn't matter because it is a constant, so c square or c just is constant. Now t square c times m, we can rewrite this as t1 by t1 square by m1 is equals to t2 square by m2, that is equals to constant. Now let's substitute the values. T1 square is T1, what is T1 here? 2 seconds. 2 square divided by m1, that is m, m1 is m, which is equals to T2 square, that is 3 square by m2 is m plus 2. Now rewriting this yields 4m plus 2, that is equals to 9m. Now rewriting this 9m minus 4m, that is equals to 8, which leads to 5m equals to 8, where m is equals to 8 by 5, that is 1.6 kg. The correct answer is option B, 1.6 kg. Let's have a look at this question. A short column of external diameter d and internal diameter small d carries an external load W. The greatest eccentricity which the load can have without producing tension on the cross section of the column is. Now there is a column whose external diameter is d and internal diameter is small d. Now there is a load W acting away from the center. The distance between center and line of action of that force is let's say E, which is eccentricity. Now if we draw the free body diagram for this, there will be two loads acting on the column. One is axial load W at the centroid and bending moment due to eccentricity, which is equals to W times E. Now the maximum stress sigma max acting on the column is equals to the stress due to axial load W plus stress due to bending moment M. Now stress due to axial load is equals to W by cross sectional area of the column plus the bending stress. We know bending stress is equals to My by I, where Y is the distance from neutral axis. Now we have area A equals to cross sectional area pi by 4 capital D square minus small d square, and Y is equals to capital D by 2, I is equals to pi by 64 times capital D power 4 to small d power 4. Now substituting all of them, and we know M is equals to W times E. So M is equals to W times E. If we substitute, sigma max equals to W by pi by 4 d square minus small d square plus M is W times E, Y is D by 2 and I is pi by 64 times capital D power 4 to small d power 4. Now sigma max is equals to 4W by pi times d square minus small d square plus here W times E times capital D by 2 divided by pi by 64 times d power 4 minus small d power 4, which is equals to My by I. Now for maximum eccentricity without producing tension on the cross section of the column is, in order to find that, we need to equal sigma max to 0. So if we do that, then 4 times W by pi d square minus d square is equals to minus WE d by 2 times pi by 64 d power 4 minus small d power 4. Now W gets cancelled here, then pi gets cancelled, 2 1s are 2 32s are, then we will have 4 divided by pi is cancelled, so no pi here, 4 divided by d square minus d square, that is equals to 32 times small e, that is eccentricity, d divided by d power 4 minus small d power 4 can be written as d square plus small d square times d square minus small d square. Here this one gets cancelled, both sides, d square minus d square, d square minus d square. Now 4 1s are 4 8s are. We will have E is equals to d square plus small d square by 8d, 8 capital D. The correct answer is option C, capital D square minus capital D square plus D square by 8D. Let's have a look at this question. If the radius of wire is stretched by a load doubled, then its Young's modulus will be. The correct answer is option D, none of the above, because elastic modulus or Young's modulus is a material property. Unless we change the material, it remains same for the given material. So it doesn't matter whether you increase or decrease the load or change the geometry. If the material is same, its elastic modulus remains same. So the correct answer is option D, none of the above. Let's have a look at this question. Longitudinal stress in a thin cylinder subjected to internal pressure is. We need to find longitudinal stress in a thin cylinder subjected to internal pressure. Here in the figure shown, there are two stresses. One is circumferential stress and another one is longitudinal stress, which acts along the axis of cylinder. Now if we write equilibrium equations for this, in circumferential direction sigma fx is equals to 0, then circumferential stress sigma h, which is acting on the cross sectional area here, that is length of the cylinder times thickness top and bottom. So it will be 2 times length of the cylinder into T is equals to the internal pressure acting on the projected area of the cylinder, that is this area, which is equals to length times diameter. Therefore internal pressure times length into diameter of the cylinder. So here L gets cancelled. Now sigma h is equals to PD by 2T. This is hoop stress. Now if we calculate the longitudinal stress, then the stress acting in the longitudinal direction is equals to sigma L. It acts throughout its circumference, so sigma L times pi d, the circumference of the cylinder, pi d into thickness pi dt, that is equals to the longitudinal area, which is this one, total area, internal area of the cylinder, that is pi d square by 4 times internal pressure acting in the longitudinal direction. Therefore here d gets cancelled, pi gets cancelled. So sigma L is equals to PD by 4T. So from this we can clearly write that sigma L is equals to sigma h by 2, that is half of the hoop stress. Option A is correct answer. Let's have a look at this question. Maximum deflection in cantilever due to pure bending moment M at its free end is. We have a cantilever beam and pure moment m is acting at its free end. So if we draw the bending moment diagram for this, it will be a rectangle over the length of the beam, which has magnitude of bending moment m given at the free end. Now the deflection delta is equals to area of bending moment diagram times centroid of the diagram. So area is m times L and centroid of rectangle is L by 2 times 1 by EI, that is equals to ML square by 2EI. Correct answer is option A, ML square by 2EI. Please do subscribe to the channel for more interesting videos.